Hello and welcome everyone. My name is Peter Robinson. Today I'm going to talk about performance overhead of atomic cross-chain transactions. So atomic cross-chain transactions is a technology that allows composable programming across private Ethereum blockchains. So it allows for inter-contract and inter-blockchain function calls that are both synchronous and atomic. So if one part of the function call fails, so one part of the overall transaction fails, then the whole call graph of functions is rolled back. And this talk is overall about the overhead of using this technology compared to just using single blockchain function calls. So I'm going to explain the technology. So before we get into it though, let's talk about scenarios. And so, in what situations would you use a cross blockchain function call? So imagine you have a hotel and train situation where you have hotels having one blockchain, train having another blockchain, you've got two travel agencies. And so you have a booking system that is wanting to book a hotel room and a train seat and have them both go through or not go through. And so this system of lockable and non-lockable contracts that we've got here would allow that to happen. Or maybe you have a supply chain situation where you have some detailed information that needs to be kept private for the supply chain participants on the logistics blockchain, the supply chain blockchain. And then maybe you've got the provenance blockchain, which is aimed to show customers information about when products move or things change. So there's two levels of privacy and information sharing, where you're sharing more information in the provenance contract and you've got more privacy in the logistics contract. Or maybe you have an Oracle contract. So you have a business blockchain and it needs to read information from an Oracle blockchain. So it's just requesting information. So how do atomic cross-chain transactions work? So they are nested Ethereum transactions and views. So a transaction is a function call that updates state, and a view is a function call that returns a value but doesn't update state. And so, for instance, you can imagine you have an originating transaction that calls a subordinate transaction that in turn calls a subordinate transaction and a subordinate view. And so the subordinate view is returning a result. And you can see on the right-hand side of this slide how you have this nested structure where this view and the transaction are signed transactions contained within the subordinate transaction, which is contained within the originating transaction. And when the transactions are created, you need to know the values that the functions are going to be called with. And so if you imagine, say, function B here, which calls to function C and function D, then if you know that parameter 1 is going to have the value 1, and you know the current state of that blockchain, then you know that function C will be called with a value 5. And if you know how function C works in its state, then you might know that it will return 6 to val. Though you should note, of course, that if the state is a different value, then the different functions get called. And so the signed transactions that need to be created are different. And so the processing of the views and transactions is you process all the subordinate views and you dispatch them to other blockchains and you get results and you cache those results. Then while you're executing the code, if you've got a subordinate transaction function call, then you check that the expected and the actual parameters match. Similarly, you do the same for subordinate views, and you return the cached result back to the code as well. And then you execute the code as normal. So if it makes the whole way through, then you dispatch all those subordinate transactions. So one of the key technologies used in this is BLS threshold signatures. And so the idea of BLS threshold signatures is that you can have a set of signers who sign some information, and then as long as M of N signers have signed the data, then you can create a group signature, and then you can verify that group signature with a group public key. So one public key is used to verify that some N group of M of the total N number of signers have signed the data. And so this threshold signature scheme is used to prove information came from a specific blockchain. And so in our scenario, you could imagine that you've got on blockchain B, it needs to be certain that the nodes on blockchain C that are, were called in for function C, that results really are the results for that function call. So when the code on blockchain B is processing the results, it needs to be sure that the information really came from blockchain C and it's a valid result. So you use threshold signing for a set of validators to sign that result. Similarly, on node A, it needs to be certain that, say, blockchain B has actually committed its updates, because it might not want to commit its updates unless blockchain B commits its updates, and similarly the other way around. And so threshold signing is used to prove that the information is ready to be committed or has been committed. So walking through a transaction, you have an externally owned account that submits a cross-chain transaction with a timeout. And then a start message is created and submitted to the coordination blockchain. So in the coordination blockchain, you've got a contract and it hosts these messages and keeps an overall view of state. And then you have you trial execute the transaction, the transaction on the root blockchain, and then you've got a subordinate transaction which you dispatch, and then you mine that that root transaction, and then the act of mining it locks that contract, and then you dispatch a subordinate view which does a trial execution. You threshold sign the result and return it, and then you might need to get the public key from the coordination blockchain to verify the result. And then you do your trial execution, you fire off your subordinate transaction, which again does a trial execution. Those contracts or those transactions get mined, contracts get locked, and then ready messages are threshold signed and sent back to the root blockchain. So this is a way of saying to that originating blockchain, hey, we're ready to commit. And at that point, the validators on the originating blockchain threshold sign a commit message. And then that commit message goes into the coordination blockchain on the coordination contract on the coordination blockchain. And then there is it fires off a message to all the other blockchains saying, hey, you should check commit. Check to see if this message should be, if all the transactions should be committed. And then signaling transactions are sent on each of the blockchains to get the updates to change, to lock in. So if one of the trial executions fails, then an error message gets returned, and then on the originating blockchain, a threshold sign ignore message is submitted to the coordination contract. And then any of the locked contracts are unlocked, and signaling transactions are sent. And it doesn't really matter where the failure occurs or if there's the timeout occurs. So if the commit message is submitted after the timeout, the coordination contract will always indicate ignore. And in that case, when the check, ignore, commit message is sent to the other blockchains, they'll check the coordination contract on the coordination blockchain, and then they will ignore the update. So they'll do a signaling transaction and then discard the provisional state updates. So performance, how does all of this perform? So the big difference turns out to be BLS threshold signatures. They are in fact, it's the verification of the signatures. Signing doesn't take so long, but it takes 5 milliseconds to verify a signature. So then the question comes, well, how many BLS signature verifications are needed? And it depends on which node you're on. So the coordinating node, so the node that's originating the transaction, or another node on the originating blockchain, or are you on a subordinate blockchain at one of the other nodes? So, and if it's a view or a transaction. And so the performance then also comes down to what is occurring in the application. So it depends on our usage scenario. So you can see the different types of transactions that are used depending on the scenario. So we got a baseline for Hyperledger Besu, which is an Ethereum client written in Java. And using this configuration here, we were able to get 375 transactions per second using just for a single blockchain transactions. So then based on that rate and the number of BLS threshold signatures needed, and the fact that they take 5 milliseconds each, I've worked out that the actual transaction rate for the scenarios is going to be what's shown here. Now, the big thing to see is that if you're on the coordinating node and all transactions emanate from that one node, it's slower than if it's across multiple nodes. So if you had multiple nodes that were all emanating cross-chain transactions, you end up with a higher transaction rate. So in summary, atomic cross-chain transactions provide atomic synchronous inter-contract function calls across blockchains. But this complex technology comes at a cost of performance. And so for the hotel train scenario, you go from 375 non-atomic single blockchain transactions per second to 39.5 transactions per second if all the transactions are instigated on the one node, or approaching 65.2 if you can distribute the node that the transactions start on. And the performance depends upon the application, so the number of subordinate transactions and views involved in the cross-chain transaction. Future work. So I've come up with a layer 2 atomic cross-chain transaction technology. And so that means you don't need to change the Ethereum client software, whereas this technology I've described does. It's also probably going to have different performance implications. To have a look at the source code that's been developed for this. So we've got a fork of Hyperledger Besu and a fork of Web3j, plus a lot of sample code. So thank you.